All right, today we're diving into something that is quite literally re-engineering the invisible world all around us. We're talking about metamaterial antennas. It's a technology that is completely changing the game for wireless communication.
You know, you've probably wondered this, right? We all want our phones, our smartwatches, all our gadgets to get smaller, sleeker, and do more stuff. But there's this fundamental roadblock, and it's not just about batteries. It's about a basic law of physics that affects one of the most important parts inside every single wireless device: the antenna.
Okay, so let's get right into it. With a normal, conventional antenna, the rule has always been super simple. Size is everything. To catch a specific radio wave, your antenna has to be a specific size. If you shrink the antenna, you basically kill its performance. We've just hit a physical wall. But what if you could invent a material that just doesn't follow those rules? A material that's literally engineered to bend the laws of physics. Well, that's where metamaterial antennas come in.
So here's our game plan. First, we're going to really dig into why this antenna problem is such a big deal. Then, we'll look at the three kind of superpowers that metamaterials give us: making antennas disappear, boosting their signal, and stopping them from interfering with each other. And finally, we'll see what this all means for the future that's being engineered right now.
So first up, the antenna's big problem. See, as all our devices get smaller and we try to pack more and more tech inside them, the space left for the antenna just keeps shrinking. And that creates a huge challenge for engineers.
Now, engineers have a specific name for these: electrically small antennas, or ESAs for short. These are the tiny little antennas inside our earbuds, our wearables, you name it. But like we said, when you shrink a regular antenna this much, it just stops working well. You get a really weak signal, you waste a ton of energy, and your bandwidth, how much data you can handle, just plummets. It's like a triple threat to good performance.
So, how in the world do you solve this? Well, this brings us to the very first superpower of metamaterials: just incredible miniaturization. This is the whole key to making antennas that are super tiny without making them terrible.
So how does this magic work? Okay, one of the most clever tricks is something called a zeroth order resonator. The best way to think of it is like a physics cheat code. Engineers build this special structure that basically makes the radio wave inside it behave as if its wavelength is, well, infinite. And this is the genius part. That trick completely decouples the antenna's operating frequency from its actual physical size. All of a sudden, you're not limited by lengthening.
And this isn't just some wild theory. It has a massive real-world impact. Using this exact technique, one research group made an antenna that was 61% smaller than a conventional one that did the exact same job. I mean, that's not just a small improvement. That's a total game changer.
And it's not a one-trick pony either. Other metamaterial patterns, like these tiny etched spirals, have gotten an even crazier 76% size reduction. Another design created a tiny antenna that could handle 3 different frequencies at once and was still 90% efficient. We're talking about fundamentally breaking the old limits here.
But look, size isn't the only issue. We also need really strong, clear signals, right? Especially for things like 5G or satellite communications. So how do you boost a signal's power without building some giant satellite dish? Well, that leads us to our second superpower: gain enhancement.
You know, the concept here is actually beautiful in its simplicity. You just take a standard antenna and you place a specially designed metamaterial layer. Think of it as a lens right over it. This lens acts like a magnifying glass for radio waves, gathering up all that energy and focusing it, which dramatically boosts the antenna's performance.
The first way to do this uses something called zero-index materials. So imagine a normal antenna radiating energy out in all directions, kind of like a bare light bulb. A ZIM lens takes all those messy, scattered waves, and it reshapes them into a single, highly focused directional beam. It's almost like turning that light bulb into a laser pointer.
Okay, method number 2 uses what are called artificial magnetic conductors. Think of an AMC surface as the perfect mirror, but for radio waves. You place it behind an antenna, and it makes sure that every last bit of signal energy gets reflected and sent in the right direction. It can effectively double the signal strength right where you need it most.
The third method, and probably the most sophisticated, uses graded index lenses or GRIN lenses. Picture these as a stack of different layers, kind of like pancakes, where each layer bends the radio waves just a little bit differently. This gives engineers this incredible, precise control to shape and even steer a radio beam, which is absolutely essential for advanced 5G networks.
All right, So we have tiny antennas and powerful antennas. But what happens when you pack a whole bunch of them really close together, like inside your smartphone, which might have 6 or more? Well, that brings us to our final big problem, and our final superpower, isolation.
When you put antennas too close to each other, their signals start to bleed into one another. Engineers call this crosstalk, and it's a huge problem. It's kind of like trying to have 5 different conversations in a tiny, crowded room. Nobody can hear anything clearly. And it's a massive issue for technologies like MIMO, which actually depend on multiple antennas working together in perfect harmony.
So, the key is figuring out what's causing this mess. And it turns out, for antennas on a circuit board, the main culprit is something called surface waves. This is basically just rogue signal energy that travels along the surface of the board itself, leaking from one antenna to the next.
And the solution is just so elegant. By placing very specific metamaterial structures in the empty space between the antennas, you can create these invisible barriers. They act just like soundproof walls, but for radio waves. They completely block those surface waves and effectively isolate each antenna from its neighbors.
And how well does it work? Well, by placing just one of these little metamaterial resonators right at the spot where the interference was worst, researchers got a 30 decibel reduction in that unwanted coupling. Now, 30 dB might not sound like a lot, but because it's a logarithmic scale, that is a 1,000-fold decrease in interference. It's a massive, massive improvement.
So let's bring it all home. We've seen these 3 incredible superpowers, making antennas smaller, stronger, and keeping them from talking over each other. What does this actually mean for us and the tech we use every single day?
This really sums it up perfectly. The miniaturization superpower. It solves the physical size limit, and that gives us the next generation of tiny IoT devices and wearables. Gain enhancement. It tackles weak signals, and that powers everything from our 5G phones to advanced radar systems. And isolation. It stops that signal crosstalk, which is what makes the complex antenna systems in our phones and routers actually work.
So the big takeaway here is this. Metamaterials are not just some small incremental step. They are a total paradigm shift. They are fundamentally breaking the old rules of antenna design, and that's paving the way for devices that are smaller, more powerful, and way more reliable, all at the same time. This isn't science fiction. This is the real engineering that's building our connected future.
And that really leaves us with a fascinating thought. This technology gives us the ability to design materials with properties that just don't exist in the natural world. It lets us engineer reality itself on a fundamental level. So the question really isn't just about antennas anymore. It's, with this power, what should we build next?